All right, so second semester final exam review guide for ChemX. Let's take a look here. It says electron structure review. No questions on the final, but you do need to know how to get valence electrons for Lewis dot structures. So oxygen, you're going to find oxygen on the periodic table. Go up. V1 is, or VI I should say, is 6. So that's 6. Phosphorus, 5A, 5. Calcium, 2A, 2, and nickel. Well, all the guys in here in the D subshell have 2 because 4s2, 5s2, 6s2 all come before the D, so they are all 2. So, bonding, it says classify each of the following as ionic, nonpolar covalent, or polar covalent bonds. So the range goes from 0 to 0.4. That is nonpolar. From 0.4 to 1.9 is polar, and then 2 and greater is ionic. So you have to find each of the elements, subtract them, and see where that lies in here. And each bond has to be checked for this. So CO, C is 2.5. This is actually O right here. Should be an O on that. Is 3.5. 3.5 minus 2.5 is 1. 1 is polar. CSO, CS is 0.7, 3.5, right? So what we take 3.5 minus 0.7. One sec.
It's 2.8.
2.8 on the line is greater than 2, so that is ionic. The other way we could do this is a metal and this is a non-metal. X minus X is 0, so that's going to be nonpolar. O minus O, nonpolar. And H minus N, 2.1, and 3.0, that's 0.9, so that's going to be polar. A bond between H and O is polar covalent. Which element has the partial positive charge? So we look at H and we look at O. O has a 3.5 for the electronegativity. Electronegativity is a pool of the electrons in that direction. So basically, if this one's higher than this one, it's going to pull the electrons toward O. If we write that out, like for example water, we would see that the electrons go towards the O. This little plus means that this is going to be a partial positive for the H. So H would have the partial positive. A bond between N and C is polar covalent. Which element has the partial negative charge? So you look at N is 3 and C is 2.5. So it's going to be pulled towards the N. Since the electrons are being pulled towards the N, it's going to get the partial negative charge. This little sign means partial. Sketch Lewis structures for AsCl5. Let me grab some paper. So AsCl5. So we're going to take a look here. As is in the center because it is unique. Cl, 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 Cl. So we look at As on the periodic table. As has 5. 5 plus 1, 2, 3, 4, 5 times 7, because chlorine is in group 7A. 5 times 7 is 35, plus 5 is 40. So now we have to make sure everything has, we have 40 electrons in this. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. If we had extra electrons, they would go on the AS in the middle. Extra electrons always go on the center. If we don't have enough electrons, then we would need a double bond somewhere in here. But that is AsCl5. That is 1, 2, 3, 4, 5 bonds, 0 unshared pairs. So that is trigonal bipyramidal. SO3, SOO. We have 6 times 4. 6 times 4 is 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. The fact that we have 26 showing means that we only have 24 available, so we need a double bond. We need to pick one of these O's, and anytime we put a double bond in there, we need to take away electrons from the atoms that we put it with. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That equals that. And the fact that we can put this double bond anywhere means that this is going to show what we call resonance. Right? And we should show it with all the places that it could possibly be. Excuse me. We have 1, 2, 3 bonds and 0 unshared pairs. So that is trigonal planar. Pretty cool. NOF, NOF. Since we have NOF, we know that O likes 2 bonds, N likes 3, and F likes 1. This is called honk. If you have carbon, carbon's going in the center. If you have nitrogen, and nitrogen's going in the center. So we're going to put nitrogen in the center. We've got O. Some of us can see in the future, and I said that oxygen likes 2 bonds. So what we're going to do is we're going to bond that twice. And 5 plus 7 is 12, plus 6 is 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2 bonded atoms and 1 unshared pair is bent or angular. And the angle there is 104.5. Angle here would be 120. Angle here, there's a bunch of them. 90, 180, and 120. NHF. The fact that we have this charge of +1 means that this needs to go in brackets. The other plus idea is that since it's plus, we actually lose 1 electron. So 5, 6, 7, 8, 9, minus 1 is 8, 2, 4, 6, 8. This is tetrahedral, which is 109.5 degrees angle. If this were a minus sign, we would add electrons instead of subtracting them. Give the shape and bond angle to each above. We did that. Describe the type of hybridization on the central atom of each above. Hybridization, basically you count S, P1, P2, P3, D1. Remember, sp3, since you have 1 s orbital and 3 p orbitals, basically these form an sp3 hybridization where they don't take the shape like normally this is spherical and this is a dumbbell shape. When they hybridize, all of these basically become the same shape. After P is D, and there would be 5 of these, but we normally only talk about sp3, D2. So you just count sp1, P2, P3, D1. sp3, D1. Here, sp1, 2, 3, sp3. Here, double bonds don't count. So you have 1 here, S, P1, P2, sp2. Here, same thing, sp1, P2. Basically, you look for areas of high electron density, and that's where those electrons are held. If the molecule has dipole moment equal to 0, then how is the molecule described? If the dipole moment is equal to 0, it is nonpolar. Basically, for something to be polar, you have to have pools of electrons in one direction. Are these molecules polar or nonpolar? Even if these bonds are polar, you have one pulling up, one pulling down, and then these three pulling at each an angle out. So this would be nonpolar for sure. SO3, same thing since it's trigonal planar, nonpolar. NH4, well, again, even though these aren't right angles here, they're 109.5, those are going to be pulling separate of each other, so that would be nonpolar as well. If we look here, this one is probably going to be polar. There's going to be a pool of electrons away from the nitrogen, and this is not linear. This is bent, so it's going to be pulled down this way and that way. So definitely it would be polar. Name the 3 types of intermolecular forces of attraction in order from strongest to weakest. The strongest is hydrogen bonding. The next strongest would be dipole-dipole. This is when you have polar molecules. And then the last one would be dispersion forces. everything has dispersion forces. Basically, if you have electrons, you have dispersion forces. What are the primary attraction forces between water molecules? That would be hydrogen bonding, because water has an oxygen on an H. Ethanol, again, actually it's just 2 carbons, C, and then on there is an OH. So again, here we have that hydrogen bonding. There'd be some extra H's on there. We won't take the time to write them, because once we know that OH is on there, then it's going to be hydrogen bonding. Oxygen molecules, we know that whatever 3.5 minus 3.5 is going to be 0. So that's just going to be dispersion forces between a polar molecule like arsenic trichloride and another polar molecule. If you have polar and polar, polars will dissolve in other polars. That is dipole-dipole. We say that likes dissolve likes. Dipole-dipole. Name the following compounds. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's going to be hexane. And 1, 2, actually we'll number from here. 1, 2. So that's going to be 2, 2, dimethyl. And right here, 1, 2, 3, we're going to have 3 instead of ane, since this is a double bond. We'll change that to hexene. 2,2-dimethyl 3-hexene. Or you could say 2,2-dimethyl hex 3-ene. Here we have something cyclic. This is cyclobutane. It's bute because 1, 2, 3, 4. And coming off of one of them, 1, 2, 3. That would be propyl cyclobutane. You don't need a 1 there because it would just be assumed that it could be anywhere. The compound 3,4-diethylhexane is a structural isomer of something else. So structural isomer means they have the same formula. So we could sit here and figure this out, but the other thing is we have diethyl. So each ethyl has 2 carbons. So that's 2 plus 2, which is 4, plus 6, which is 10. That's 10 carbons. Since it's an ane, we can figure out the rest of the formula by H's. It would be 2 times 10, which is 20, plus 2. So we're looking basically for C10H22. If we look here, this is decane, that's C10H22. Phenylethene, we don't have to worry about any of that. Pent, not enough. A dimethyl would be 7. Tribenzyl. So benzene is a ring of 6, so that's going to be way bigger than that. Which of the following is true for alkynes? Alkynes mainly means we have a triple bond. They contain both carbon-carbon double and triple bonds? No, just a triple bond. They are unsaturated. They contain only sp3 hybridization. A carbon triple bond is not sp3 hybridization. That is sp, p1. So nope, a carbon double bond would be sp2, 1, 2, sp1, p2, and just a carbon like from an alkane, 1, 2, 3, 4, sp1, 2, 3, sp3. So nope, yep. Unsaturated means it doesn't have the maximum number of hydrogens it could have. Since we have a double bond, it doesn't have the maximum number of hydrogens it could have. Bonding practice and final exam type questions. Select the correct molecular formula for Ni3. Ni. So I'm looking at trigonal planar or probably tetrahedral. 5 plus 21 is 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 3 bonds, 1 unshared pair would be tetrahedral. I'm sorry, trigonal pyramidal. Tetrahedral arrangement, but 1, 2, 3 bonds, that's a triangle in a pyramid because of the lone pair. Tetrahedral arrangement, but trigonal pyramidal shape. Select the correct one for this one. IF4, 1, 2, 3, 4. This would be tetrahedral unless there are extra lone pairs we're going to put on the center. 7 times 5 is 35. This negative one means we're going to change it to 36. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So that's 1, 2, 3, 4 bonds and 1 unshared pair. That's going to be square planar. The Lewis structure for CHCl3 shows a total of 9 lone pairs. So there we got 2, 4, 6, 8, 10, 12, 14, 16, 18. 1, 2, 3, 4, 5, 6, 7, 8, 9 lone pairs. True. In the Lewis structure for ICl2, how many lone pairs of electrons are around the central iodine atom? ICl2, negative. So we have 7 times 3 is 21, 22, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. There are 3 lone pairs around the iodine atom. Remember, any extra lone pairs go on the central atom. Which of the following would be polar molecules? CCl4 will not, because they're going to cancel each other out. pH3, we got to look, is a pH bond polar or nonpolar? 2.1, 2.1. That's going to be 0, so that's nonpolar. Even if they were polar, it would be a polar molecule. CO2, they're going to pull each other and cancel each other out, so nope. NH3 for sure. What type of hybridization is utilized by the NH3? Well, NH3 would be this right here. 1, 2, 3, 4, sp1, 2, 3, sp3 hybridization. Which of the following substances would you expect to have the highest boiling point? So we're looking for things with the highest intermolecular forces. That would be OH, because that has hydrogen bonding. This is dipole-dipole because of the oxygen there. This is simply dispersion forces, and this is dispersion forces. Sometimes we call those London dispersion forces. Which of the following substances would you have the highest vapor pressure? So vapor pressure, the less intermolecular forces, the higher the vapor pressure, because you don't need a lot of pressure or vapor pressure to keep something that's holding itself together down. So we're going to be looking for the one with the least forces. Between these two, both have dispersion forces, but there's a lot less electrons here. So that's going to be a lot of less electrons being used. Name the molecules following the IUPAC system rules. 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be octane. 1, 2, 3, 4, 5, or 1, 2, 3, 4. So it's going to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Doesn't matter which way we go. We're going to have 1, 2, 3, 4, 4, 5. We're going to have 2, 4, 5, 7. 4 is tetra, methyl, octane. Here we have 1, 2, 3, 4, so that's butane. Here's the deal with this: since these are opposite of each other on the double bond, this is going to be trans. So 2, 3, dichloro. Trans. That's not butane, it's butene because of that. Trans 2 butene. 1, 2 butene. Right? 1, 2, 3, 4. 2, 3. Dichloro, since there's 2 of them. 2 trans because they're opposite. If they were the same side, then it would be cis, but trans because they're opposite. 2 because that's where the butene, the ene is. 1, 2, 3, 4, 5, 6, 7. So it's going to be a heptene. Remember, the double bond takes precedent to get the lowest number. 1, 2, 3. So that's 3 heptene. On that third is an ethyl. 1, 2, 3 ethyl. Ethyl comes before methyl. 1, 2, 3, 4, 5, 6. 6 methyl. 3 heptene. Oh, wow, big one here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's going to be nonene. Again, that has to get that the lowest number. 2 ethyl. 3, 4, 5. 5 ethyl. 6, 7. 7 methyl. And we also have 6, 5, 4 methyl. Remember again, ethyl comes before methyl, so 2, 5 diethyl, 4, 7 dimethyl, 1 nonene. There we go. Solutions chemistry. So this is going to be molarity, molality, percent by volume, all those different things. It says, what is the molarity of a solution that contains 15 grams of magnesium chloride in 50 milliliters of solution? So molarity is moles per liter. So from this we can take 15 grams, get that to moles, and we can take 50 milliliters and get that to liters. Every 1,000 milliliters is 1 liter. And every 95.2 grams is 1 mole. 15 divided by 50 times 1,000 divided by 95.2. A little slow today. 15 divided by 50 times 1,000 divided by 95.2.
Sorry, could you say that again?
Nope.
My apologies.
Yeah, we already went with the calculator. So we get 3.15. And that's our answer here. The density of the above solution is 1.35 grams per centimeter cubed, which means milliliters. Calculate the molality, mole fraction, and mass percent. So the density of the above solution is this. So we're going to go ahead and let's do the mass first. We know we have 15 grams. We got to find the total mass of the solution. We have 15 grams of this. We can find the percent by mass first. We know that we have 1 liter of the solution, and that is 1,000 centimeters cubed or milliliters. Every 1 centimeter cubed is 1.35 grams. 1,000 times 1.35.
The answer is 1,350.
So 1,350 grams, and 15 grams of that is our magnesium chloride. 15 divided by 1,350 times 100.
It's approximately 1.1111.
1.11% is by mass of the magnesium chloride. So that was easy enough. So this also allows us to find the mass of the entire solution, which is 1,350, and if we subtract the mass of just the magnesium chloride, we can find the mass of the solvent. 1,350 minus 15.
The answer is 1,335.
So that's the mass of the solvent. We can change that to kilograms because every 1,000 grams is 1 kilogram, and molality is moles per kilogram. So again, if we start with 15.0 grams and 1.335 kilograms of the solvent, every 95.2 grams is 1 mole. That will give us the molality. 15 divided by 95.2 divided by 1.335.
The answer is approximately 0.118.
0.118 would be the molality, moles per kilogram. Now we just need mole fraction. So we'll go ahead and find the moles of the solvent and the solute. So 15 divided by 95.2.
It's approximately 0.1575.
And remember, this is part divided by total. So we need to add the moles of the water as well. Well, we know that the grams of water is 1335. 1335 divided by 18.02. 1335 divided by 18.02.
It's approximately 74.0843.
74.08. Remember that this minus this, since this is the total mass, minus the 15 grams, that's the mass of the water. The molar mass of water is 18.02. So we get 74.08. 74.08 plus 0.15756.
It's approximately 74.2375.
74.238. 0.15756 divided by 74.238.
That would be approximately 0.002122.
That's the mole fraction. Easy enough. How many grams of KBr would be present in 5 liters of a 0.28 molar aqueous solution? So we want grams of KBr. And this is liters and this is moles per liter. So we're going to start with liters because that is 1 unit. Every 1 liter of the solution has 0.28 moles of the KBr. And every 1 mole of the KBr is equal to 119.0 grams. 0.5 times 0.28 times 119.
It's 16.66.
16.66 grams. Be able to define solute. Solute is what is dissolved. Solvent does the dissolving. So solubility, how much dissolves. "35 grams of NaCl, that's the solute, dissolved in 100 grams of H2O. That is a solvent at 30 degrees. If we increase temperature, more of the salt will dissolve. Be able to describe and recognize solutions of concentrated. Concentrated means large amount of moles of solute, large amount of solute. Dilute, that means that we've added solvent or large amount of solvent to solute. Saturated, that's the max amount that you can have dissolved. Supersaturated, that is above the max amount. That's made by heating it and allowing it to cool slightly. This is anywhere below max amount. How does dissolving an electrolyte differ from a non-electrolyte? An electrolyte breaks apart. Call that dissociation. For every 1 mole of NaCl, you get 1 mole of Na particles and 1 mole of Cl particles. Non-electrolytes like C12H22O11, like sugar, it's just one thing. You know this because this is ionic. It starts with a metal. This does not start with a metal. So for every 1 mole of this, even though there's a bunch of moles of atoms in there, it does not separate. It holds itself together. As temperature increases, how does solubility of most solids dissolved in water change? It increases. Solubility of gases. As temperature increases, the solubility of gas decreases. That's why in the summertime we have fish kills, because the amount of oxygen dissolved is lower. As pressure of a gas increases above the surface, what happens to solubility of gases? It increases. That's why a carbonated soda, always when you open it, it makes that noise because that's under pressure. Colligative properties. How does adding a solute affect the boiling point of a solvent? Boiling point is elevated. Freezing point is lowered. That's why we put salt on the roads in the winter. Ionic solutions of greater molecular solutes because of the index, because of them separating into the different number of particles. And it only matters how many moles of particles are involved, not, like 1 mole of sugar versus 1 mole of NaCl. 1 mole of sugar is only 1 mole of particles. 1 mole of NaCl is 2 moles of particles. 1 mole of Na and 1 mole of Cl. How does it affect the vapor pressure? So if you add a solute, the particles will hold themselves. They get trapped more. So the vapor pressure will actually go down because it won't require as much pressure on the surface to keep that holding itself together as much. 1.6 grams of naphthalene is dissolved in 20 grams of benzene. Benzene normally freezes at 5.51 and its KF value is 5.12. What is the freezing point of the naphthalene benzene? All right, so we're going to jump down here real quick. So the formula for this is delta T sub, are we boiling? Nope, we're freezing. Delta T of F equals the index times the molality times the KF. The index for this, since both of them are, you know, this is the actual solute is not ionic, this is 1. The molality of this, we're going to go ahead and find out here, 1.60 grams over dissolved in 20 grams. So that's I'm gonna go ahead and change that to 0.020 because molality, remember, is per kilogram, moles per kilogram, and we just need to this is kilograms. We need to change this to grams. Every so many grams is 1 mole. So 10 times 12.01 plus 8.08.
It's 128.18.
1.6 divided by 0.02 divided by 128.18.
It's approximately 0.6241.
So that's going to be the molality, 0.624 moles per kilogram. And then if we take a look, this is kilogram per mole, degrees Celsius, kilogram per mole. So what's going to happen here is those are going to cancel out, and it is 5.12. 1 times 0.624 times 5.12.
It's approximately 3.1948.
So that's going to be the change in freezing point. So if we know that it normally freezes here, since the freezing point is depressed, we're going to add that to that. 3.19 plus 5.51.
The answer is 8.7.
So that's 8.7 degrees Celsius. There won't be an osmotic pressure on the final, so we won't bother going over that. Let's take a look at these practice problems, and we'll finish up with solutions, I think, in this video. Next video, we'll cover rates in equilibrium. So a solution of hydrogen peroxide is 30% by volume, or by mass, and has a density of this. What is the molarity? So it's 30.0 grams of H2O2 by mass, right? And if it's 100 grams total, every 1.1 gram is 1 centimeter cubed. Every 1,000 centimeters cubed is 1 liter. 100 divided by 1.11 divided by 1,000.
It's approximately 0.09009.
So there's our liters. We're going to take 30.0 grams. We need to change it to moles. Every 1 mole is 2.02 plus 32. .30 divided by 0.09 divided by 34.02.
It's approximately 9.7981.
That's going to be 9.798, which would be 9.80, but this looks like it's going to be the closest to that answer for our work. A solution containing 296.6 grams of magnesium nitrate per liter has a density of this. The molarity is this. So this is a trick question because they give you the density, but you don't need it. So 296.6 grams per 1 liter. I got to change from grams to moles, and then I'm done. So we have magnesium, 24.31. We have 2 times 14.01, which is 28.02, and we have 6 times 16. 6 times 16 plus 28.02 plus 24.31.
It's 148.33.
296.6 divided by 148.33.
The answer is approximately 1.9995.
And that's going to be, for us, close to 2. What volume of a 0.58 molar solution contains 1.2 grams of solute? So we're looking for volume, and it's in milliliters, so that's 1 unit. I'm going to start with 1.28 grams. I need to change that to moles. And it's calcium chloride, 40.08 plus 35.45 times 2.
The answer is 110.98.
So there's the molar mass. Every 1 mole in this solution has 0.580 moles for every 1 liter, and every 1 liter is 1,000 milliliters. 1.28 divided by 110.98 divided by 0.58 times 1,000.
It's approximately 19.8855.
It's going to be 19.9 milliliters. We're not going to have a vapor pressure one on the final exam, so we don't have to worry about that. You do need to know what vapor pressure and osmotic pressure, like what happens. So vapor pressure goes down, boiling point goes up, freezing point goes down, and osmotic pressure. Remember, that's the pressure required to prevent the solvent from going through the membrane. The pressure is going to go up the more the solvent that we have. So it's decrease, increase, decrease, increase. Remember the snail, if you put salt on it, we need a high pressure in our earthen atmosphere in order to prevent that liquid from coming out. And as we know, that liquid comes out. Poor snails, right? So I think that will do it for us. Don't forget that all the answers to this are on this back part. You can always check that. The next video we'll discuss rates and kinetics and equilibrium. And then the final video will be acid-base and oxidations. So this will be a 3-video series. Thank you very much and have a great day.